let's discuss briefly what is it all about, radioactive decay. It's actually very easy. It's the easiest chapter in the book, I think. You know, when some heavy nuclei, which have, like if you look in the periodic table above lead, like starting from bismuth and beyond, which are big nuclei. And when they're big nuclei, they have also lots of neutrons and so on to keep some stability there. But in reality, these big nuclei, the bigger they are, the more unstable they are. And when they are unstable, they can break, they can chuck out pieces, small pieces. And this is a phenomenon that we call radioactivity. So because they are unstable, they decay. We call it decaying when they emit small particles to become more stable. So these particles that they emit, all the unstable nuclei, can be three types. One is the alpha particles, the next type is called beta particles, and the last is called gamma particles. They were called alpha, beta, and gamma because when they were discovered, when radioactivity was discovered, they didn't know about what particles they were. In fact, at those times, they didn't even know about the electron. So they call them alpha, beta, and gamma because they behaved differently. And in fact, they could distinguish between the three types of radiation emitted by the way they could penetrate materials. So the first type of radioactivity, the alpha particles, could not penetrate, not even a piece of paper. A piece of paper would stop them. So these they would call them alpha particles. Then the next type of particles, the beta particles, could penetrate a few millimeters of aluminium. So this is how they could distinguish from the alpha particles. And the last type of radioactivity, the gamma particles, or gamma rays, they could go through a thick piece of lead before they stopped. I mean, there was need of like 1 meter of concrete to stop this type of, actually they call them rays. So this is how they distinguished initially between alpha, beta, and gamma, depending on their penetrability through matter. Of course, later on, don't want to go to details, you can read this stuff. Now we know that alpha particles are actually helium nuclei. And helium has 2 protons, and this type of helium is this nuclei is called an alpha particle that has 2 protons and 2 neutrons, altogether 4 nucleons. So these are the alpha particles. The beta particles, well, at least the ones that you need to know at your level, it's like electrons. The electrons. The truth is that beta decay can be also with other particles, positrons and so on. But you need to know that the beta minus decay, which are the electrons. So we know that beta particles are electrons, and the gamma are actually gamma rays, like in the form of electromagnetic radiation, like the X-rays or the visible light. So these are gamma rays. We just call them gamma rays up to today. But we know that these are it's an electromagnetic radiation, much like the X-rays. But whereas the X-rays are emitted by an atom due to the electrons that orbit the nucleus, the gamma rays are emitted from the nucleus, from within the nucleus. So they have more energy. Okay, so these are the 3 types of radiation. Now these are the types, the radiation emitted by nuclides that decay. Now let us see, how do we write these decays? How do we represent these alpha, beta, and gamma decays? Now, here I have, actually this is from the lesson, I think it's week 34, isn't it? The last week where it's about the radioactive decay. So the alpha decay, we said that usually the nuclides actually, that decay by alpha emission are actually the heavy ones, which are bismuth and beyond. Actually, bismuth has a Z of 83. I should correct this. From bismuth and beyond, Z82, I think it's lead, isn't it? Yeah, where's the periodic table? Lead is 82. But nevertheless, bismuth starts from 83. Bismuth and beyond, we consider them like heavy nuclei, big nuclei. And these tend to decay, if most of them are unstable, and they, because they're heavy, actually they emit an alpha particle. Okay, so alpha decay is happening mostly to heavy nuclei beyond Z83. And so we said the alpha particle is actually a helium nucleus, a helium 4. So this is the alpha decay. Now, this is an example of an alpha decay. Let us see what we must, if we are to write the decay of a certain nuclide, like uranium-238 here. Uranium-238, you see it has an atomic number 92, which is bigger than 83. It's most likely to decay by alpha emission. Now, it decays, it chucks out an alpha particle, here it is, and here is this thorium-234 is what remains. So by emitting this alpha particle, the energy, it becomes more stable. Well, of course, this new nuclide that forms after that it remains actually after the emission of a helium might also be radioactive, and it will also decay by emitting probably another alpha particle. But nevertheless, we don't care about that. Let us look at this decay of uranium and see how do we know that this will be a thorium. Okay. So let me remove all this. I tend to make a mess. Yeah. Let us see. How do we write an alpha decay? The important aspects to begin with is that we need to know that the charge, the conservation of charge and the conservation of mass laws need to be observed. So we have the conservation of charge. Charge must be conserved during a decay, and also the conservation of mass must be observed. Those two important laws. Now, the charge, how is it represented in this decay? What are the charges now in the nuclei? It's the charge of the protons, isn't it? So these numbers here, which represents actually the atomic number of this nuclei, of all these items here involved in the alpha decay. This 92 for uranium, for example, represents 92 protons, isn't it? And remember that protons are charged particles. So, and they have, if we have 92 protons in the uranium, the initial parent nucleus has 92 protons. Obviously, this charge of the 92 protons has to be conserved when the nucleus decays and becomes thorium plus a helium atom, which means 92, which represents 92 protons, or 92 times the elementary charge, isn't it? This 92 must remain, must be equal to 90 plus 2, which represents, the 90 plus 2 represents the charge that, the resulting charge of the species that will be produced. This is the 90 protons from the thorium, and these are the 2 protons from the helium particle that is emitted, the alpha particle. So you see, if these numbers now, 92 must be equal to the number of protons of the products of the decay. So this, in other words, this kind of expression here represents the conservation of charge during the decay. Now, something similar happens with the conservation of mass. Now, for the conservation of mass, we will look at the top numbers, which are the mass numbers of these nuclides. here, the 238 of uranium that we see on top of the uranium 238 means that this uranium has 238 nucleons, which the number of nucleons actually represent the mass of the uranium 238, isn't it? So this mass has to be conserved as well. Therefore, this number up there must be equal with the mass numbers of the products. So 234 for thorium. I hope you can see the, maybe I should make it a little bit bigger so you can see it clearly. Okay. You see, 238 must be equal to 234 up there plus 4, plus 4. And this expression now corresponds to the conservation of mass. So this is what we do. The conservation of mass is when we take the quality of the mass numbers of both the item that decays and the products, the daughter and the particle that is emitted, and the conservation of charge. We do the same with the atomic number, the number of protons, in other words. Okay, trying to make some space. All right. So this way, if we have this in mind, the conservation of mass and the conservation of charge, we can figure out, when we know, for example, that we have uranium and it decays by alpha emission, we can figure out the daughter produced. There's no need to give it to us in the equation. We can figure it out by ourselves because we know what is the parent. It's uranium-238 and it decays by alpha emission. Obviously, what remains, we must have these numbers, this atomic number and this mass number up there, 90 and 234. And remember, if we know the atomic number, if we know that the atomic number is 90, we go into the periodic table and we see what element here has a atomic number 90. Here's the periodic table. We look, and it's thorium, so it cannot be anything else, isn't it? So this is how we find, we can figure out the daughter produced. Okay, so this is the alpha decay. Something in a similar way, we're going to reason about the beta decay. Beta decay is a decay that usually beta decay is undergone by smaller nuclei, not this big above bismuth, but it's not like a fixed rule that big nuclei do not emit beta particles. That's not true. But usually beta decay, which is more common, is the decay of the smaller, the medium-sized nuclei that have too many neutrons and they're not very stable because of all these neutrons there. And so these nuclei, these smaller ones, like look at this carbon-14, for example, decays by beta emission. And again, how do we write the equation? We write the daughter and the beta particle, which is an electron, we said. Now, again, during this beta decay, the law of conservation of mass and the conservation of charge has to be conserved, exactly as we saw in the alpha decay. So here is the beta particle, okay. Now, in order for us to help us write down the two laws, the conservation of mass and the conservation of charge, instead of writing the electron like simple as this one, like we usually represent the electron, to help us with our calculations, we write the electron like that. So if we have this electron, the particle, the electron, of course, the electron does not have any protons, isn't it? It has zero protons, but it has a charge. And the charge of the electron is equal to, equal numerically to the elementary charge, which is the same as the charge of a proton, but it has a negative charge, and therefore we represent it with a -1 there to represent its charge, like -1, elementary charge. So this number down here would represent the charge of an electron. And what can we write up there which corresponds to the mass number in the way that we represent the various nuclides? Well, up there usually is is the mass number of whatever species we have. All these numbers here, the top numbers, correspond to the mass number. But now an electron is a tiny little particle that we usually ignore its mass. So we assume that it does not have any mass, and we write there a 0 representing its mass. So that is why we write it in this way. We show it in this way in the beta decay. And now in this way, like, in other words, here I have written it ready. Now it's easier for us to see if the two conservation laws that we have to consider are observed. Like, okay, so 6, in this decay of carbon 14, we have the charge must be conserved. So 6 on the left-hand side is the charge of the 6 protons of the carbon. On the other side, the total charge must also be 6. So we see here, we are given already the daughter, it's nitrogen, which has a charge of 7, representing the 7 protons, and -1 here from the charge of the electron. You see, 7 minus 1 makes 6. So we see that the conservation of charge is observed, isn't it? Because this makes 6. Now the conservation of mass, we take the top numbers. 14 nucleons for the carbon 14 must be equal to the mass numbers of the products. So 14 for nitrogen plus 0 for the electron. We see again that the mass, the law of conservation of mass is also conserved. I hope you can see that, okay? Okay, so once again, if we don't know the nucleus produced after our initial unstable nuclide decays by beta emission, by considering the law of conservation of mass and charge, we can figure out which nuclide this will be, isn't it? So it's not necessary that they will give it to us. We can figure it out. They can ask us to find which nuclide it's going to be. So, okay, why do I do that? The last type of decay is the gamma decay. The gamma decay is not really any, the gamma decay being electromagnetic radiation, it's not really that there is a particle that has a mass or a charge. You know, it's like visible light, like a photon of a different frequency than that of visible radiation. So we can represent the gamma decay, the gamma particle, like a photon, with 0 both mass and charge numbers, isn't it? Because it's just electromagnetic radiation, which means the parent nucleus, when it emits gamma rays, it does not really change. It just, its energy drops from being excited when it is when it has too much energy, more energy than its ground energy level. It emits some gamma radiation and gets rid of some energy and becomes more stable. Usually, you don't actually need to know this. It's not in the book. It's not in the curriculum. But for extra interest, I think it's nice. I mean, there's no change, in other words, in the original nuclide. It just gets rid of some energy by emitting some gamma radiation and drops energy. But it's the product, can we say the product? It's not really a product. It's the same really nucleus, isn't it? Just with at a lower energy level. So just to complete the 3 types of radioactive decay, the alpha, beta, and gamma. So I hope it's not too hard. If you want me to repeat something, if something is unclear, please let me know. Now let's see, what is the question? Does that mean for alpha decay, the lowest it can decay into, is thallium 81? You mean No, we said it doesn't mean that below Z82 it's not allowed to see an alpha decay. Yes, it can be decayed, but I mean most chances are that it is the heaviest nuclei that usually decay by alpha emission. The majority, in other words, of decays that we can expect from the heavy nuclides will be alpha decay, but there will be some beta decays as well. And I have never met a case where you have a small or no nucleus decaying by alpha emission. Okay, so when you are now at 81 at this kind of atomic numbers, yeah, you can still have some alpha decays for sure, but I mean not so often. And I just want you to understand that roughly when a nucleus is too big, it cannot be stable because the nuclear force that keeps the nucleus together cannot reach from one side of the nucleus to the other. So it's easy to have instability there, and it's easier to emit an alpha particle and drop to some lower energy level by changing. It's called transmutation, this change. But remember, there are not clear rules like if you have a atomic number 81, you're not allowed to decay by alpha emission. So no, don't take it like that so strictly. Okay, just an idea. What about thallium? Yeah. Maybe if we have time, if we continue some other time with this radiation, maybe I can show you some radioactive series and you can see where the alpha decays happen more often than the beta decays as we go further down. All right, but now there's no need to talk more about that. Okay, so these are about the radioactive decays. Another aspect that you need to know from this last topic is actually the half-life, the concept of half-life, which is the time it takes for half the initial nuclei to decay. But perhaps it's better if we see it in problems. Let us look at some problems. Okay, look at this. It's from a past exam from 18. Let's do this question here. Thorium-234, here it is radioactive. It decays by beta emission. You see, they have it decaying by beta emission, though big nuclide. We would expect it with alpha anyway. So it decays by beta emission to form an isotope of protactinium, which is, this is the symbol of the element. Complete the nuclide equation for this decay. Okay, so they tell us that it decays by beta emission, which means to assume that this is an electron. Here is the beta particle. How do we symbolize the electron? What charge do we give it? -1, -1. And what mass do we give it? 0. All right. So now, since we have the particle and we know the initial nuclide that decays, we can find actually the atomic number and mass number of protactinium. They didn't even have to tell that it's a protactinium. We could find it in the periodic table. All right, so let's see what are these numbers there. So if we take conservation of charge first, let's start with the 90 must be equal, the atomic number. The 90 must be equal to this number that we don't know, which is x, let's call it x, plus the charge of the electron, the beta particle, which is -1. So, which is, this is x -1. All right, so what must be the value for x then? If we solve for x here, is 90 plus 1 is 91, isn't it? So this should be 91 here. And if we are not sure, we can even look in the periodic table and find where is 91 in the periodic table. And here we are, and it is protactinium. We are correct. So Now we need to find the mass number of protactinium of this particular isotope, this particular nuclide. Now we have to take the conservation of mass. 234, which is the mass number of thorium, must be equal to this unknown number. Let's call it what? Y. Let's call it Y plus 0. And obviously then Y is 234 again. So you see, when we have a beta particle emitted, the mass number stays the same as it was in the original nuclide. So there we have it, the numbers of protactinium. It's its atomic number is 91. Its mass number is 234. Oh, there is about half-life. Let's read this question and see how. Let's make it bigger. Okay. A pure sample of thorium, thorium-234, emits beta particles at a count rate of 2048 counts per second. And the half-life of thorium-234 is 24 days. Now, what does it mean? It means that, say that we have a sample of a big chunk of thorium-234. It's radioactive and it decays and it emits electrons, beta particles. It means that if we have, I don't know, X nuclides of thorium-234, after 24 days, we're going to have only half of them left. This is the meaning of the half-life of this radioactive isotope. That means because they say that the half-life of thorium is 24 days. It means every 24 days, half of the initial nuclei in the sample have decayed. And we have only the other half left. And after another 24 days, the other half will have decayed. And after another 24 days, another half of the remaining half has decayed. So if initially we have 2,480, say, undecayed nuclide, after 24 days, we are going to have half of this number, which is how much? It's 1,240, isn't it? After 24 days. After another 24 days, we're going to have half of this, which will be, what is this, 620, isn't it? 620. And after another 24 days, we're going to have half of that, which is 310, and so on and so forth. So this is the meaning of the half-life. Every so many days, which is the half-life of this particular nuclide, we're going to have half of the remaining initial nuclides undecayed. So in this case, now let us see in this example, they don't tell us we have so many nuclides initially, but they say when we start counting for the first time, we count 2,480 counts per second. It's a measure of the decay of this thorium-234. So the half-life of thorium-234 is 24 days. Okay, that means that after 24 days elapse and we count again, we're going to count only 1,240 counts per second. The same sample will only give us these counts because half of the initial nuclides have decayed. So, all right, now let's see. Calculate the count rate of the emission of beta particles from the thorium in the sample after 72 days have passed. Okay, so after 72 days, how many counts are we going to get? What counts are we going to get? Now, 72 days, if we divide it by 24 days, which is the half-life of thorium-234, you see 72 days divided by 24, which is the half-life of thorium-234, actually is 3. which means 72 days corresponds to 3 half-lives. All right, so how many counts do we expect? If initially we had 2,480 counts, after 1 half-life, we'll count only 1,240 counts per second. And after a second half-life, we are going to count 620. And after a third half-life, we are going to count 310. So this is the counts that we're going to count after 3 half-lives. So our count rate after 72 days, which is 3 half-lives, will be 310 counts per second. So we do this question just because it's in this paper, but if necessary, we need to discuss a bit better about half-life. So, oh dear, 12 o'clock, all right. Okay, we have to continue again next week, and we are going to practice our alpha, beta, and gamma decays and questions on this.